Okay, question A says, describe qualitatively using words and diagrams the difference in the object's speed at point B if the twirling is done at a constant speed or if the tension is kept constant. So what would result in a greater speed? So first thing we got to do is just wrap our heads conceptually around what's happening here with the physics. So let's just take a look at some forces. I'm going to draw some stuff on here and then erase it. Okay, we will agree that gravity always operates straight down. So at any of these points that might be of interest to us, gravity always operates straight down, which means in a situation like point A, there is a, I guess I'm not going to write it that way. At point A, down here, there's a lot of, gravity is providing an additional centrifugal force, right, pointing outward. That gravitational force is not going to present anything here because it's perpendicular. Now, gravitational force actually works opposite the centrifugal force up here. So you can start to see, just looking at gravity, the fact that it's always pointing down, and that the total tension in the rope is going to vary depending on where it is in the circle. Again, just because gravity, and sometimes on this section right down here, gravity is going to be adding to the centrifugal force, that force outward. And up here at the very, very top, it's going to be taking away, right? So we have to just account for all that stuff. And I'm going to erase all this. Okay. So now let's maybe get a little bit more in depth with what's happening. If it's done at a constant speed, so A and B, let's take a look at the tensions for A and B. So let's just start with part A. Let's just start with A. At A, we have tension going up this way. That's providing the centripetal force. We have mg going down like this. But we also have the centrifugal force, which is going to be mv squared over r, going down like that. And so the tension at A is going to be a combination of those two things, mg plus mv squared all over r. All right, so it's going to be a combination of those two things. At point B, the tension, again, is the centripetal force. We will have some centrifugal force outward right here. And we're going to have gravity going down like this. So the gravitational force mg, there is some component of it that works this way. Not all of it, obviously, but some of it does work that way. So the tension at B is going to be a combination of these things. It's going to be, now mg sine, so the component of the gravity that works this way is going to be mg sine 30. That's this, the one I have drawn in as dots. So the tension at B is going to be mv squared over r minus this mg sine 30. Sine 30. Okay. So you can see that the tension, now keep in mind right now I'm trying to consider that the v is constant, because that's for part A, for part 1 it does say constant speed. But the tensions will not be equal. So now so that's the qualitative description using diagrams and symbols. So there will obviously be no speed difference at point B if the twirling is done at a constant speed. However, the tension is constantly changing. Now, what if for part 2 we have a constant tension? Well, that would indicate that now if you have in order to keep a constant speed, you have to have a change in tension. If you switch it and say, now we're going to have a constant tension, of course there's going to be a change in speed. So now the question is B going to be faster or slower when you have a constant tension than part A would be? So let's take a look at these things going on. I'm going to start by solving, since, let me rephrase it. I'm going to take this equation right here and rewrite it. TA minus mg equals mv squared over r. I'm going to rewrite this one over here. TV plus mg sine 30 equals mv squared over r. Okay. Remember, this is in the case of the constant velocity. So TA minus mg equals TB plus mg sine theta, 30, not theta. Again, because if they're both equal to mv squared over r, and the v was constant, and m and r are both constants, this is true, which means that the tension at point B is going to be equal to TA minus TB constant. And if we keep TB equal to TA constant or the same, then the tension at point B is going to actually be quite a bit higher than it normally would, because you don't have to subtract off this term anymore, right? If you're just saying this is equal to this, then this whole term goes away, which means that the tension would be higher. If the tension is higher, taking a look up here, if this tension increases, and this part hasn't changed, and this isn't changed, and this hasn't changed, if you increase this, the velocity at B has to go way up. I shouldn't say way up, it has to go up, right? Because if you're keeping everything else the same, but you've increased the tension at B, that means the velocity has to increase. So what would result in the greater speed at point B? 2 would, because again, the tension would be increased. The fact that we have a rope with mass now means that if I were to redraw this, we have this object that wants to fly off this way, but it has to drag all this mass with it, all right? So there's a couple ways to think about this thing. One is you could get all fancy and use angular momentum, and you could figure out the addition of this mass. What is now the new what is the new moment of inertia for this system? Because we have a point, we have an object with a mass right here. You could get that by going mvr equals L. Here we could take the center of mass of this rope, add it into the whole thing, but we don't need to do that. Instead, all we got to do is think about this. That this object has a greater mass now because it has the object plus the rope. Now, normally for projectile motions, the mass was irrelevant. Here, however, take a look at the center of mass of the system. The mass was irrelevant early on projectile problems because we always considered the entire mass to be localized at one point. Here, if you have a rope with a mass on it, that means that the center of mass of this system is no longer at the object's position. It is somewhere in between. And let's just, for argument's sake, let's just say it's right here. Notice that this distance right here, this position right here has less height than that position right there. So you actually have less initial energy, less initial potential energy going into the system because the center of mass position is lower vertically. Another way you can think about this is think of the average velocity. The velocity here is going to be a max. The velocity at the very, very center is 0. So that means that there has to be a range of average velocities for all these pieces, but the average velocity of all these pieces, while it might be difficult to calculate it with calculus, it's not difficult to understand that the average velocity is going to be less than if all of it was located right at that position right there. So not only do you have less potential energy, you have less average velocity, which means you have less kinetic energy. So the addition of the rope will decrease the range. Straight up, pretty easy idea. When twirling the object at constant speed, explain in terms of work and energy how the constant speed is maintained. Is the path truly circular? That one's a difficult one to think about. But which forces are doing positive work and which forces are doing negative work? Okay. Let's zoom in over here. Yeah, whatever. Okay. So if the object is being twirled at a constant speed, let's think about it right here for argument's sake. An object right here. You have kinetic energy, you have velocity in the positive direction, but you have gravity in this direction, so we can maybe go like this. We have, by the way, this is not supposed to be a force diagram. I'm not trying to draw, I'm just drawing what's going on here. We have velocity is up, we have gravity going down. Again, those aren't the same units, so I'm not drawing a force diagram. Now, the other force, there is a force going on here. Maybe, you know what, maybe I will just adjust this for a second. I will make this a force diagram. If you have these forces going on, tension going into the side, mg going down, some centrifugal force outward. As the object, and maybe this is, I'll just color code it. As the object moves up like this, gravity is always going this way. So there's always a component of gravity doing negative work, right? Because the object's velocity is this way, gravity opposes that. So at the top, this top half right here, gravity is always doing negative work. That is very sloppy, I'm sorry. On the bottom part, maybe I should switch the color here. On the bottom part here, notice that gravity is always going to be causing this thing to speed up in the direction that it is currently going, right? So here's a velocity here in this case. And so gravity is doing positive work. If we want to keep this velocity a constant as it goes all the way through, the tension has to be basically whatever work the gravity, I'm going to go back to this top half right here. If gravity is doing negative work, then the tension that you need to, basically the work that the tension has to do is has to cancel out the negative work done by gravity. So tension is doing positive work up here. So tension, positive work. Again, and I want to point out that these are always, the direction and the angles of these are always changing. I'm just doing totally conceptually here. Yes, there are different components because of different angles and things like that, but just in general, the top half, gravity is doing negative work, sometimes more than others, more work than others, depending on the position. And the tension is doing positive work, because those things have to cancel out if you want the velocity to always be constant. Likewise down here, if gravity is doing, I didn't even say positive. If gravity is doing positive work down here, that means that the tension must be doing negative work down here. Again, because we need those things to cancel out, we need the net work to be zero. If you're maintaining a constant velocity, that means that you're having no change in rotational kinetic, or no change in kinetic energy in this case. So the work needs to cancel. It has to cancel. So whatever gravity does, tension has to undo it in the other direction. So is the path truly circular when the speed is maintained? All right, this is a little bit more difficult. I'm going to give a very conceptual wishy-washy, or not a wishy, but very conceptual abstract answer to this, because it doesn't ask me to prove it mathematically. So what I am about to say, I am not able to prove mathematically, but I'm just going to make an argument for it. Notice how these angles are always changing, all right? So let me just switch to another color. The interplay between gravity and tension is very simple in the straight up and down positions and also at the side-to-side positions, right? It's very easy to calculate. All the way through here, however, the angles are constantly changing, so the interplay, or the net result, is always more complicated than at the top, bottom, and side positions. So the tension, the tension that you're providing is not going to be constant, right? Because since gravity is constantly changing the amount of work it's doing, the tension must be constantly changing the amount of work it's doing. Sometimes you need to apply more, sometimes you need to apply less. That adjusted tension, remember the tension is what causes the circular path. If you are adjusting the tension constantly on the way up and on the way down, I'm going to say that the circle is not going to be a perfect circle.